In this video, we look at various metrics that aid in assessing and enhancing the maintainability and robustness of your code base. Understanding these metrics and how to interpret them provides a framework for developers aiming to produce high-quality software. Let's begin by distinguishing between quantitative and qualitative criteria used to evaluate internal code quality. Quantitative metrics are numerical values that provide objective insights into aspects like complexity and test coverage. These can be automatically measured using tools such as SonarQube or CodeClimate. On the other hand, qualitative criteria encompass subjective aspects like readability, modularity, and adherence to coding standards. These are typically assessed through code reviews and rely on the judgment of experienced developers. By combining both quantitative and qualitative assessments, we can achieve a comprehensive understanding of our code's internal quality. While these metrics provide valuable insights, it's essential to approach them with a critical perspective to fully understand their implications. Cyclomatic complexity, introduced by Thomas McCabe in 1976, measures the number of independent paths through a program's source code. A higher value suggests a more intricate code structure, potentially complicating understanding, testing, and maintenance. The formula is M equals E minus N plus 2P. E represents the number of edges in the control flow graph, N denotes the number of nodes, and P stands for the number of connected components, which is typically one for a single program. For instance, a simple function without control flow statements has a cyclomatic complexity of 1. Introducing an if statement adds a decision point, raising the complexity to 2 due to the additional path. While it's generally recommended to keep cyclomatic complexity below 10 to maintain code simplicity, this threshold isn't universally applicable. Some functions may inherently require higher complexity due to their nature, and overly simplifying code to meet an arbitrary threshold can lead to less efficient or less readable solutions. Cognitive complexity assesses how challenging code is to comprehend, by considering factors like nested control structures and recursion. Lower cognitive complexity is desirable as it indicates code that's easier to read and maintain. Although SonarQube has published a white paper that describes how to calculate it, this metric is not well known and may be interpreted subjectively. This example from SonarQube illustrates the intuitive value of the measure compared to cyclomatic complexity. The Maintainability Index combines various factors, including cyclomatic complexity, lines of code, and Halstead volume, into a single score indicating how maintainable a codebase is. A higher score suggests better maintainability. The Halstead volume is a deterministic method for calculating code complexity based on operators and operands. As a composite metric, Maintainability Index offers a broad overview, but it can sometimes obscure specific issues within the code. Relying solely on the Maintainability Index without examining its individual components might lead to overlooking critical areas needing improvement. Test coverage measures the proportion of code exercised by automated tests. Higher coverage can lead to early defect detection and more reliable software. However, achieving 100% test coverage doesn't guarantee the absence of bugs, as the quality of tests is paramount. Moreover, striving for complete coverage can result in diminishing returns, with significant effort required to test less critical paths. Depth of inheritance refers to the number of class levels in an inheritance hierarchy. A deeper hierarchy can increase complexity, as changes in parent classes may have widespread effects on child classes. While shallow hierarchies enhance clarity, overly flattening inheritance structures can lead to code duplication and violate principles like don't repeat yourself. Class coupling measures the degree of interdependence between classes. High coupling can complicate modifications and testing, as changes in one class may necessitate alterations in others. However, some level of coupling is natural and sometimes necessary for functionality. Striving for minimal coupling should be balanced with the need for cohesive and functional interactions between classes. Counting lines of code provides a basic measure of a program's size. While a higher line count isn't inherently negative, it can indicate areas where code could be refactored for simplicity. Conversely, overly concise code can be cryptic and harder to maintain. Thus, this metric should be interpreted in context, considering the trade-off between brevity and clarity. Beyond quantitative measures, qualitative assessments like code readability, adherence to coding standards, and detection of code smells are crucial. These aspects are best evaluated through code reviews and developer judgment. However, qualitative assessments can be subjective and influenced by individual preferences, making standardization challenging. In conclusion, while internal software quality metrics are invaluable tools for assessing and improving codebases, it's essential to apply them judiciously. Understanding their limitations and considering the broader context ensures a balanced approach to software quality assessment.